This exercise, you have it on Blackboard under the section that talks about power, etc. So here's a Blackboard. If you go, I hope you can see this. Let me see if I can make it smaller. Okay, so if you go under power, okay, so this is the lecture, and then here in class, another in class, and one more in class. These are exercises that were usually done in class, and I'm gonna do them here over the video. So the one I'm doing right now is the first one right here. Okay, so it says researcher wants to compare the effect of drug X versus placebo on brain size in mice. He randomly allocated 16 mice to either drug X or placebo, and then measured their brain size after 6 weeks of daily dose for either treatment. So 16 mice, 8 they were treated with the drug. One group was treated with the drug, the other one was treated with the placebo for 6 weeks to a certain dose. And then after these six weeks, the results were as follow. The placebo group, the average mean brain size was 16 gram with a standard deviation of 12 gram, whereas the group that received the drug, their average brain size or mean brain size is 50 grams with a standard deviation of 10 grams. Is there evidence that brain size is different between the two groups of mice? So here you're asked to run a testing hypothesis and try to figure out the answer. Before you run the hypothesis, you need to know which type of hypothesis and which type of test you're going to run. And it's helpful to ask yourself 3 questions. So the first question you ask yourself is, how many groups am I comparing? Obviously, here we have two groups, the group that received the placebo and the group that received the drug. So this is the first question you ask yourself. How many groups? So let me write them down. How many groups? And the answer is 2. The second question, are the groups dependent or matched or paired or independent? And for us, if you remember for this course, we said that we're going to consider them to be paired if it's the same individual in every group. Yani here, was it the same mice in the first group and the same mice in the second group? The answer is no, these are different mice. And therefore, the answer to that question, these are independent. And the last question is the outcome variable. The outcome variable, is it categorical or is it numerical? Meaning you're interested in means or you're interested in percentages. And obviously, again, looking at what we measured, we're interested in numerical. We're interested in means. Once you answer these 3 questions, it will become evident to you that the null hypothesis that you're going to be testing is of the following nature. Mu of group 1 is equal to mu of group 2. So mu of group 1 is equal to mu of group 2. And for this to be correct, you have to identify what is the variable you're testing. And here this is the brain size. And the second question is mean group 1 and mean group 2. Okay, so group 1 are those that receive placebo, and group 2 those not receiving the drug X. To finish up your step 1, you have to write the alternative hypothesis, which is mu1 not equal to mu2. Step number 2, by now everybody is familiar with that. This is assuming that the null is true, and we set alpha at 0.05, which is equal to 5%. Now, step number 3, we're going to calculate the test. Which test are we going to use? Well, knowing that we're comparing two groups that are independent and we're interested in the means, this is the independent t-test. Okay, so it's the independent t-test. Let's calculate the independent t-test. To do so, let me just get these from here, put them somewhere else that I can look at them. Wonderful. And let's go to our uh, painting brush. Now, if you remember, the independent t-test has the following formula, which is x bar 1 minus x bar 2, and then you're going to divide the s pool, and that is 1 over n1 plus 1 over, I'm sorry, n2. This is n. Okay, so let's replace the things we already know fast. So calling group 1 the placebo, the average was 64 gram. For the second average, that was those that were treated, and that was 50 grams. And then we're going to divide. Now we're going to have to find S pooled in a minute. This is S pooled. But before we do that, I can right now write that it's 1 over 8 plus 1 over 8, because if you remember, we had 8 mice per group. Okay, so let's find the S pool. Again, what is the formula of the S pool? The S pool had a formula where you're going to actually get the sum of square from group 1. You're going to add it to the sum of square from group 2, and you're going to divide by degrees of freedom 1 plus the degrees of freedom 2. Okay, so far this is a variance formula. To turn it into a standard deviation, you just take the square root of all of this, and this is your S pooled. Now, how do we find the sum of square in group 1? You take the standard deviation of group 1, you square it, and you multiply it by the degrees of freedom. So the standard deviation in group 1 was 12. You're going to square it, and you're going to multiply it by the degrees of freedom, which was 7, plus the standard deviation in the second group, which was 10. Again, you square the 10, and you multiply it by 8 minus 1, which is 7. And you're going to divide by n1 plus n2 minus 2. So 8 plus 8, 16 minus 2 is 14. And you do the square root of all of this. And the answer to that, let me just do that real quickly right here. Okay, times 7. And this is 10 square times 7. So we add up these two values together. And then we divide by 14, and then you take the square root of the answer. All right, so I got 11.04. All right, and remember, a quick way to make sure that your calculation is correct is just compare that the S pool is actually between 12 and 10. Now remember, here we have exactly the same sample size, so we're not surprised that the S pool is not exactly equal, but very close to the average between these two. Somebody who would just add the 12 to the 10 and divide by 2 would get 11. It's not exactly, it's 11, it's 11.045. So we're going to plug the 11.045 in our formula. Now we're ready to get our T. And all right, let me do that again real quickly. So the answer I got using my calculations. So first of all, that difference right here is 14. And by taking this, which is 1 over 8 plus 1 over 8, that's 2 over 8, which is 1 over 4. And 0.25, you square root that, that's a half. So half multiplied by this, you're going to get 5.52. And therefore, dividing the 14 by 5.52, the T comes out to be equal to 2.535. Okay, and remember this T has degrees of freedom of 14. And once more, here's your T distribution. And the value that you found is 2.535. And hence the p-value is going to be that area right there multiplied by 2. The table doesn't give you that, so what you're going to have to do is to do the 1 minus this area right here, and you'll have to multiply by 2. Okay, let me see if I can get that quickly. Okay, so we're looking for 2.535 for degrees of freedom 14. Here's degrees of freedom 14 right here, and I'm looking for 2.535. This value does not exist, but what I have is a value below it and a value above it. Okay, sorry. So my t is right between these two. Therefore, if I go up and I do 1 minus and 1 minus, I'm going to get 1% on one side and 2.5% on the other side, and multiply by 2. That gives me 5% and 2%. All right, so let me go back to my actually calculation. So where was it? Right here. Okay, so the independent t-test came out to be equal to 2.535. Step number 4, we had to find the p-value, and I'm going to write the definition of the p-value. This is the probability of the t as extreme as the 2.535 or more extreme, and there's a condition that the null is true. And according to our calculation, we figured out that our p-value is between 0.1% and 0.5%. Okay, I'm going to write again here the definition of this p-value just as a reminder. This is the probability to observe a difference as extreme as the difference we observed, which is the difference between 50 and 14. So to observe a difference as extreme as the one we observed in the sample between the two groups' brain sizes, if, and in capital, that's if the null is true, معناتها if in reality there was no difference between the two groups in the population. Okay, I hope this is becoming clear. What's the definition of the null hypothesis? Okay, so what is step number 5? Step number 5, you're going to compare your p-value to alpha, and p-value came out to be less than alpha because we set alpha to be equal to 0.05, and our p-value is definitely less than 0.05. Therefore, our step number 6, we're going to reject the null hypothesis. This is also known as your statistical conclusion. And step number 7, you're going to write a research conclusion, and therefore we're going to say that there is evidence that the mean brain size between the two mice group is different, or you can say that the observed difference in brain size is statistically significant. Remember, this is like the key word here, statistically significant, meaning that this difference between these two groups actually has a reality in the population. And as such, you're done. Your testing hypothesis is done. Yeah, that's where things end. But let's see what other questions we have added to this scenario to see and if we can answer them. Okay, so it says that the researcher decided to give all 16 mice drug X for 16 weeks and then compare the brain size afterwards. So now he's not actually giving them placebo versus drug, he's actually giving everybody the drug. And how he's looking at the brain size before and the brain size after and you're actually provided the average before, you're provided with the average after, and you're provided with the standard deviation of the difference. No, that's actually the difference between the two. That's d bar. Okay, and um, and then he ran the statistical analysis and concluded that the difference observed is due to chance only. So that's one of the scenarios where I actually give you the result without you having to run any type of analysis. And based on that, I'm going to ask you questions. So first of all, before we do any kind of thing, let's think about the scenario that we have over here. What is the scenario? If the researcher decides to give all 16 mice the drugs, and then he's going to measure their brain size before and after. So you ask yourself, how many groups am I comparing? Well, it is the same mice, but you're actually looking at two variables or two conditions, the before condition and the after condition. So you actually have two groups. However, since they are the same mice, these are paired, and you're interested in a numerical outcome, which is the size of the brain. So it should be clear looking at this exercise that you're going to be using the paired t-test. Okay? All right, so using the paired t-test, the question is, what can you say about the p-value? All right, so what do we have that can help us answer this question? Let's read the last sentence. The last sentence says, he ran statistical analysis and concluded that the difference is due to chance only. شو معناتها the difference is due to chance only? Meaning that the difference he observed here between the 57 and the 50, that difference is not real. This is just an artifact of sampling. So according to his conclusion, in reality there is no difference. Yani, he's concluding that the null hypothesis is true. He is failing to reject the null hypothesis. And when would we fail to reject the null hypothesis? We would fail to reject the null hypothesis when the p-value is actually greater than alpha. Okay? What test was used and what is the requirement of the new test? Okay, so what test do we use? Actually, I kind of answered that question earlier on. Since you have the same type mice tested before and after, and you're interested in a numerical outcome, which is the size, then this is the pair t-test. Now, what are the requirements of the pair t-test? Like the t-test, the sampling distribution of the variable of interest, which is here the difference, has to be normal. So either we assume that the differences have a normal distribution, or the sample size has to be greater than or equal to 25. Now we know that the sample size is not equal to 25. The sample size is 16. And therefore the requirement has to be that the distribution of the differences is normal. So I'm going to write down the answer. We use the paired t-test, and we have to say that the sampling distribution of the differences is normal. This is true when differences have a normal distribution. So we have to assume that. Okay, question number 3. When the researcher presented his result to his colleague, she suggested, yani the colleague suggested, that he increases his sample because he could be lacking power. According to her, he made what kind of error? And can increasing sample size fix the problem? All right, so let's think about what we are told and see if we can answer the question. All right. So I'm going to write back the 4 scenarios that we have been familiar with now. So this is either the null is true, the null is false, and this is where you fail to reject, and this is where you reject. And we said this is 1 minus alpha, correct? This is the type 1 error, which is alpha. This is the type 2 error, which is beta. And this is 1 minus beta, also known as power. Okay, now according to what happened in the study, the researcher failed to reject, remember? And it could be one of two things. Either that his decision is correct or that his decision is wrong. Okay, now, if his decision is wrong, it means that he committed a type 2 error, and therefore that means that this error is too large. To reduce that error, you need to increase your power. And from what we've discussed previously, what are the things that increases power? You know that it's either the effect size, either you have to increase the effect size, or you have to increase your sample size. Well, right here, I don't think he can increase the effect size. I mean, he already sacrificed the mice. All he can do now is increase sample size. Maybe recruit more mice and like repeat the same study with 5 more mice, add them up together and have a larger sample size. That would be true. That would be true if in reality the null is false. So according to his colleague, what the colleague is saying is that, okay, although you failed to reject, she believes that he made the type 2 error, meaning she believes the reality of the null is that the null is false. She believes that mu of brain before and mu of brain after are not equal. That's what she believes. She believes that the null is false. But she believes he made a type 2 error. He failed to detect that difference. And she's recommending for him to fix that problem is by increasing the power of your study. And you can do that by increasing your sample size. Okay? And that is what happened. So when the researcher presented his result to his colleagues, he suggested that he increases his sample size because he could be lacking power. Okay? According to her, what kind of error he made? Well, according to her, he made a type 2 error. A type 2 error of failing to detect the difference. And can increasing sample size fix the problem? Yes. When you made a type 2 error, increasing sample size will increase your power and therefore fix the problem. What is the effect size in this study? The effect size, again, a very simplistic definition, is the difference observed. What is the difference observed? 7. So that is our best shot at what is the effect size in this study. Okay. All right, so let's move along and see what else do we got. A clinician is looking at the effect of long hospital stay over mood. To do so, he took 2 samples from the hospital where he worked. One sample was from patients that stayed for less than 1 week, while the other sample was from those who stayed for more than a week. He contacted them, and after receiving their consent to participate in the study, he measured their mood, namely depression, and found that the average of depression score for the first group was 12.5 with a standard deviation of 8, while the average of the second group was 19.8 with a standard deviation of 11, and you're provided with a p-value. The p-value is 0.022. By the way, this is typical when you're reading article. In articles, you will see p-value provided to you. So question number 1, what test did he use? Let's ask the 3 question. How many groups? Are they the same people? And what is the outcome? How many groups are we comparing here? We're comparing 2 groups, those that stayed for less than a week and those that stayed for more than a week. Okay, are they the same people? Obviously, no, they're not the same people. And what is the outcome of interest? Well, the outcome of interest is numerical. This is depression score. So when you meet these 3 things, the test that you use is the independent t-test. Okay, so let me write down the answer, independent t-test. Okay, what is the statistical conclusion? All right, how do we know the statistical conclusion? Reminder, statistical conclusion is either fail to reject or reject, and that is based on the p-value, whether it's larger than alpha or smaller than alpha. Let's look at the p-value. The p-value came out to be 0.022, yani 2.2%. Not provided with the alpha, you have to assume that the alpha is 5%, and therefore, based on these results, the p-value is less than alpha, and therefore the statistical conclusion is to reject the null hypothesis. What is the research conclusion? All right, so the research conclusion is going to be that there is a difference between the 2 groups. But that difference is where? Well, look at the average. The average depression for the first group is 12.5, whereas it's 19.8 for the second group. And then, therefore, the research conclusion would be that the difference observed is statistically significant. We have evidence to suggest that those that stayed longer have a higher score on depression than those that stayed shorter. Okay? What is the effect size? Okay, effect size, if you remember, we talked about the effect size being the observed difference. So here, the simplest way to write the effect size is 19.8, which is the average in group 1, minus 12.5, which is the average in the second group, and this is about 7.3. Okay, now again, this is not the actual definition, that's a simplified definition. What is the sample size? Well, a sample size is how many people did he observe in both groups together. That would be your total sample size. Does it say? Well, let me read it again. One sample, while the other sample, he contacted them and receiving. There's nothing that tells us what the sample size is. We don't know what the sample size is. Unknown. Is it possible that he made a type 2 error? Is it possible that he achieved it? Notice the question here is about possible, okay? Now we know that he rejected the null hypothesis. Let's go back to our table and let me clean up a little bit. Okay, so this is our table, and we know that in this study, the researcher rejected. Once you reject, you're either in this category or in that category. So you either made a type 1 error or you achieved power. That's it. There's no way you could have been in any other place. So let's go back and read the question. The question is it possible that he made a type 2 error? No, it is not, because type 2 error is only when you fail to reject. Since he rejected, that's not possible. Is it possible he achieved power? The answer is yes, it's a possibility, because he rejected. And definition of power is the probability of rejecting the null hypothesis when the null hypothesis is false. Is it possible he made a type 1 error? And the answer is yes, it is possible, because definition of type 1 error is the probability of rejecting the null hypothesis when in fact the null hypothesis is true. If his conclusion is correct, then the null hypothesis is true or false. Let's go back to our drawing and figure it out. So out of the two possibilities, either type 1 error or power, only power is a correct decision, whereas type 1 error is an error. Therefore, knowing that he rejected and knowing that his decision is correct, we know that that means he achieved power. And now that we know he achieved power, that directly means that the null hypothesis has to be false. So let's go back and see what the question. If his conclusion is correct, معناتها he achieved power, then that means then the reality of the null is false. The reality of the null, not the answer to this question. Reality of the null is false. Does he need an IRB approval to do this study? This is kind of like out of the scope of this course, but it's always good to know the answer to that. Yes, you always need an IRB. IRB is Institutional Review Board, and this is a board of people that are going to review your study to make sure that your study is done ethically, that you're not causing any harm to your research participants. Okay, I hope you found this application to be useful, and I'm glad you watched this video.